Thank you very much, Rostislav, for a very gracious introduction. It is a true honor to be here. As Rostislav said, I was born in this city, and I lived here until I was almost 12 years old. And we left, as it happens, almost exactly 45 years ago. It was on September 28th, 1979. And it's especially an honor to be here during this difficult time. So this lecture is on discrete, continuous, and arithmetic aspects of Fourier uncertainty. Okay, so let's begin. And so let f be a function from z and d to complex numbers. So z mod n is just integers modulo n. Z and d is a d-dimensional module over z sub n. If you don't know what a module is, just think of the grid over z mod n, no problem. And engineers insist on calling such functions signals. I have no objection. Okay? And suppose that we transmit the Fourier transform. So we take the signal and we encode it as the Fourier transform. A discrete Fourier transform comes in a variety of normalizations. And here, I choose the L2 normalization. So as you'll see, it makes the constant in the Plancherel inequality 1. Okay, I'm going to write all of this out. Don't worry. Okay. And Fourier inversion formula says that we can recover the function from its Fourier transform in a very simple and direct way. Okay? And those of you who like computers know that this algorithm is very fast. Okay? So if the whole signal gets through, we can recover the signal without any difficulty. The whole point of these lectures is to discuss the situation when some of the signal is lost. Okay? Is everybody with me? Am I speaking clearly enough? Yes? Okay, no problem. Yes?
The operation of minus and multiplication, we get transverse of the use both structure on this group? Direct.
Oh, no, it's x dot m is a dot product. So it's x1 m1 plus x2 m2 up to xd md. So, yeah, so this is the dot product. And then plus and minus is the usual plus and minus. Everything that I'm going to talk about works on locally compact abelian groups, but I don't like generalization for the sake of generalization. Okay? All right. So again, so the basic question is, can we recover f exactly from its discrete Fourier transform if some of the frequencies are unobserved? Okay? They can be unobserved for any number of reasons. Noise, interference, jamming, right? But suppose some of the frequencies are lost. And the question is, can we recover the signal? Okay? So from the beginning, it is clear that there must be some reasonable assumptions. If the whole signal is lost, you're not going to recover it. Okay? Common sense is your friend when you do mathematics. Okay? So the answer turns out to be yes. If the signal is supported on a set E and Z and D, so support of the function are the values where this function is not zero. Everything is discrete, which means that everything is simple, at least on the level of definitions. Okay? So if f is supported in E, and the size of the support, the number of non-zero values of the function, multiplied by the number of missing values, does not exceed the size of the whole space divided by 2. And the main tool is the classical Fourier uncertainty principle. Okay? All right. Okay, so there are formulas that we are going to use repeatedly. So first, Fourier inversion, that we can write f of x as n to the minus d over 2, and then the same formulas as the Fourier transform, except that there's no negative sign inside chi of x dot m. And remember, chi of t is e to the 2 pi I divided by capital N t. Okay? So it's called a character, but if you don't know what a character is, this will not hurt you at all. Okay? And the Plancherel formula, which says that the sum of the Fourier coefficient squared is simply equal to the sum of the values of the function squared. Okay? Once again, formulas like this are quite universal. They hold in Euclidean space with under suitable hypotheses, and this formula holds on any finite locally compact abelian group with the same proof. Okay, so we're going to use these over and over, and for the sake of completeness, I'm going to prove them. Okay. All right, so let's prove the Fourier inversion. So we write n to the minus d over 2 times the summation of chi of x dot m f hat of m. Okay, and now we simply plug in the definition of the Fourier transform. The trick is to use a letter other than x. My students occasionally forget about this. Okay, in lower division classes. Okay, so you plug it in. You change the order of summation. You want to sum in m first. Okay, except that one thing that really, really annoys me is when people call this Fubini. This is not Fubini. Guido Fubini was a great mathematician, and he did not invent rearranging finite sums. Okay, this was known when dinosaurs still walked the earth. Okay. Huh? Still, it just hurts me. I think that this is, I call it using Guido Fubini's name in vain. It's like, using God's name in vain is using Fubini's name in vain. Okay, no, this is just rearrangement of a finite sum. And then we sum in m first. And now this is just geometric series, okay, or orthogonality, if you will. And that inner sum is 0 unless x equals y. If x does equal to y, you get n to the d, because you're summing 1 over the whole space, and then you get a function f of x back. So this is proof of Fourier inversion. Okay. By the way, in Euclidean space, things are often mystified. Okay. And in fact, one can give the proof of the inversion in Euclidean space by using this type of an argument and a certain approximation, right? So please don't be scared of Euclidean space. It's not that scary. Okay, now proof of Plancherel, exactly the same. Okay, so here's the idea to keep in mind, and so this is another thing that I say to my students quite often, is that one of the most important techniques in mathematics is to understand that when you take a sum and you square its modulus, it's the same as rewriting it twice with a different letter. Okay? So we write out f hat of m modulus squared. You also have to not forget to take a complex conjugate. Okay? And then on the inner sum is chi of x minus y dot m, f of x, complex conjugate f of y. I think I accidentally put complex conjugate in the correct place. I usually don't. Okay. And
it's a question what place is correct.
That's true.
Physicists would object.
Oh, that's true. And physicists are people too. Yeah. Okay. And then you have n to the minus d on the outside because, okay, and then you have a sum in m. Once again, we reverse the order of summation and we don't call it Fubini. And the sum of chi of x minus y dot m we have just seen. It's the exact same argument. You get 0 unless x equals y. And if x does equal to y, we get n to the d and summation of f of x squared. Okay? So believe it or not, these two very simple ideas are going to take us a long way. Okay? So something that I've noticed in recent years is that when I was young, I wanted to convince everybody how complicated my proofs were. And now I'm trying to convince everybody that my proofs are simple. And I don't remember exactly when this transition took place, but I just noticed fairly recently. Okay? Okay, so let's make a few simple calculations. And if you like that sort of a thing, you can compute along with me if you wish. So let's take n to be an odd prime, and let's define a paraboloid. Okay? So I chose two examples, a paraboloid and a sphere. And I chose these examples for two reasons. First, for several reasons. First, they're important examples in signal recovery, and I'm going to mention why. But also, Fourier transforms of indicators of these objects are very important in Euclidean Fourier analysis as well. And I'm going to talk about that a bit later also. Okay? Everybody's still with me? Everybody's awake? Excellent. Okay, all right. So we want to compute the Fourier transform of the indicator function of the paraboloid. So it's n to the minus d over 2 times the summation of chi of minus y dot m prime plus the so-called length of y times md. But the length here is strictly formal. It's a sum of squares. Okay? But before you dismissed the sum of squares as being something artificial, it really isn't, because this quantity, sum of squares, is still invariant under the orthogonal group. Okay? So it is a reasonable analog of the usual Euclidean distance. Okay? And of course, you can replace it by any non-degenerate quadratic form, but this is not the point right now. Right. M prime, so we write M as M prime comma MD. So M prime is the first d minus 1 coordinates, and MD is the last coordinate, and Y is in Z and D minus 1. Okay?
Did you put norm without squaring on purpose?
Yes, I put the norm without squaring on purpose, even though this does occasionally annoy people, and that's okay. If you're annoyed, no. If you're annoyed, it's okay. The reason I do this is because I want to stress a particular point, and that is that taking square roots in integers modulo a prime is a dangerous business, because you can only do it roughly half the time. Okay? As it turns out, one can actually get around this problem and take a square root, but again, this is not the point. Okay? So, okay, now suppose that MD is 0 and M prime is not 0. Okay? Then we simply have a sum of characters, chi of minus y dot m, and we have already seen that this sum is identically 0. Oh, it's geometric series. It's geometric series that loops onto itself. So it really is on that level. Okay? And so if MD is not 0, then let's consider the case M prime is identically 0. Then we have a summation of n to the minus d over 2, summation of chi of minus md, the so-called length of y. And this is just a product of the classical Gauss sums. Okay, so this is really one of the most important sums in analytic number theory, for example. And this is, so G of A is a summation of chi of AT squared. Okay, this is a classical Gauss sum that was estimated, not just estimated, it was analyzed very thoroughly by Gauss in the early 19th century. Okay. Right? So let's estimate the Gauss sum. Okay, so one of the things that I would like to do in these lectures is to actually expose you to techniques, not merely go over the concepts. Okay, and this is a, yes. So suppose that n is an odd prime and a is not 0, then we take the modulus of g of a and we square it. Okay, so then we get a sum over t and s of chi of a times t squared minus s squared. Let me stress that if I lose you at any point, you can just raise your hand and say, please explain this. This will make me very happy. In fact, if this doesn't happen at least twice in every lecture, I'm going to have a funny feeling in my stomach. So please ask me, even if you don't have a question, ask me anyway, just to make me feel better. Yeah. Okay? So you have chi of a t squared minus s squared. Then this is equal to the summation of chi of ATS. This is rotation by 45 degrees. Or more precisely, you just set, yeah, right. You just replace t minus s by t and t plus s by s. And here's an interesting point. Okay, so this is more of a comment on American educational system than the system here. But in the US, we teach students integrals before we teach them sums. I could talk for hours how stupid that is, right? But so since we teach them integrals first, an immediate instinct is, where is the Jacobian? There is no Jacobian. This is a bijection. Okay? I'm sorry?
What?
Well, the oddness is just means that we are in a field, so everything is invertible. But yes, if it were not a prime, then we would encounter a Jacobian. Then it would not necessarily be a bijection. But over a field, this is a bijection, and we can do it. Okay? So now what do we do? And this is another instructive point in this proof, is that we have a sum in two variables, right? Okay, just like we've learned in multivariable calculus that we can't really do anything with multiple integrals, we need to reduce them to a single integral, right? Because the human brain is too small for multiple integrals, right? So how do we reduce this to a single integral? Okay, we go not into polar coordinates, but if you wish, hyperbolic coordinates. We set TS equal to U, and we sum in U on the outside, right? In other words, the moment that you notice that in a multiple sum or a multiple integral, everything depends on a single parameter, this tells you that you should do this, okay? Right, because there's only TS over there, so you set TS equal to U, then you sum in U, and this is just equal to the summation of chi of AU, n of U, where n is the number of solutions of the equation, TS equals U, the number of pairs TS, where TS equals U. Okay? So suppose that U is 0. Then how can T times S be 0? Well, T is 0 or S is 0, but then you need to not double count. So it's 2 times capital N minus 1, right? Suppose that U is not 0. Then neither T nor U can be 0. You have N minus 1 choices for T, and S is determined.
Because it's prime.
Because it's prime, because it's a field, right? And so N of 0 is 2N minus 1, and N minus 1 otherwise. So we plug it in. G of A modulus squared is 2N minus 1 plus N minus 1 times the summation over U not equal to 0 of chi of AU. And then we get capital N plus, so we incorporate the 0 frequency. Capital N plus N minus 1 times sum over all of the U's. And that sum is 0, because once again, we're summing all the characters. So this geometric series wraps around, right? And then we get capital N. And we just established a classical Gauss. Of course, anytime. Sure.
You told us that you are...
Uh-huh.
Okay. Can you hear me?
I can hear
you. Okay. So you told that it is second equality, where you told that you are just rotating 45 degrees, yes?
Well, but this is a figure of speech.
I know that this is a figure of speech, but the question is, let's assume that T is equal 1 and S is equal 1, yes?
Yes.
And you are rotating. Suppose that you have two-dimensional vectors, yes? One vector is has coordinates 1 minus 1. Second coordinate has coordinates 1, 1. Yes? Both vectors have the norm square root of 2. When you are rotating them, you should get...
okay.
Maybe I'm wrong, but you should get 2 TS, not 1 TS.
I understand the issue. Yeah. So let's put it differently. Set T prime to equal to T minus S. Okay? And set S prime to equal to T plus S. Okay? And then you can simply solve for T and S in terms of T prime and S prime. And the game is over.
Okay, thank you.
No worries. No, I'm very happy. You owe me at least one more question. Because questions asked by these gentlemen don't count. All right? So the modulus of G of A is square root of n. So now let's go back to the paraboloid. If n is an odd prime, then we see that if we have zeros in the first d minus 1 coordinates, then what do we get? We have n to the minus d over 2, summation of chi of md times the length of y, which is n to the minus d over 2. because we're computing the modulus. So there really should be a modulus on the second half of the inequality. Okay? It's a theorem that there are typos in every set of slides, no matter how many times you check them. It doesn't converge. Okay? So it's a modulus. So you have n to the minus d over 2, root n to the power of d minus 1, which is capital N to the power of minus a half. Okay? And here the question we should ask ourselves is, how close are we to victory? Okay? Now, m prime is identically 0. What happens if m prime is not 0? Then we get linear terms. Okay? But if we have linear terms, we can get rid of them using this very mysterious technique. I discovered that it's mysterious every time I decide to punish myself and volunteer to teach calculus for non-majors. And that is completing the square, right? So by completing the square, we can get rid of the linear terms, okay? And we obtain the same bound, right? There's literally nothing to be said there. You complete the square, you change variables, and you reduce to this case. It's very, very difficult to go wrong. Okay? Does this make sense? Is everybody with me? Yeah? Okay. All right. So what happens in the case of a sphere? Okay, and this case is incredibly fascinating to me for reasons I'll explain. Okay? In Euclidean space, right? In Euclidean space, so those of you who've sort of seen these things before, if you want to compute the Fourier transform of a measure in a paraboloid or the sphere, or at least estimate it, it's more or less the same calculation. It reduces to first-year calculus, integration by parts, and there's really no problem. Okay. However, in the discrete setting, when even when n is prime, the calculation of the paraboloid case already required the estimation of a Gauss sum. And that is not so difficult, but this is already, I claim, requires perhaps at least as much sophistication as the estimation in the Euclidean case. But in the case of the sphere, we are going to very quickly run into a very scary object, okay? And so what do? We write the indicator function as n to the minus d, sum of chi of minus x dot m. And here, what we do is we sum over s not equal to 0, chi of s, length of x minus 1. So why can we get away with this? If we sum over all s, then this is going to place us on the sphere, okay? The reason we can sum over s not equal to 0 is because if s is 0, then the previous sum is identically 0. Okay? So we are synthesizing the delta function on the sphere, if you want to use fancy language, which is not necessary. Okay? So now I actually wrote out that completing the square step, because I recently taught calculus for biological sciences majors, so I'm used to this procedure over and over and over. Okay? So, and if you plug this in, what we arrive at is capital N to the minus d over 2. By the way, do you see why this 1 over n is here? This is because if s is 0, the sum collapses. Okay? All right. So what we arrive at is the following expression. It's n to the minus d over 2 minus 1, summation over s not equal to 0, summation over x, and now we have Gauss sums hiding in there. So it's chi of s times the length of s, x, chi of minus s, and chi of minus the length of m over 4s. So the scary object has not yet been identified. We need to chisel away a few more things. So we use the Gauss sum estimate, and what we get is 1 over n, summation of gamma to the d of s. The modulus of gamma of s is 1. We just showed this when we estimated the Gauss sum. And then we have chi of minus s minus length of m over 4s. Okay? Now you can actually estimate the Fourier transform of a measure in the sphere by following this procedure. You don't have to, but you can. And if you have to estimate this integral, you can do this using integration by parts. But you're not going to estimate this sum using integration by parts, because this is the celebrated Kloosterman sum that was finally where the sharp estimate was obtained by André Weil, and it's one of the greatest achievements of 20th century mathematics. Okay, so this is an illustration of how things can get much, much uglier in a discrete setting. Okay, so
Ask if the people here know.
Oh yeah, this is actually a good, this is an interesting sociological study. How many people in the room have heard of André Weil? Okay, it's not many. So one thing that I strongly recommend is just look him up on Wikipedia. A truly, truly great mathematician. And in fact, technically, the result he obtained in 1948 doesn't even cover this case, because he did it in the case where there is no term gamma to the d to the s. This term was handled within a decade by Salih. This is why these are called Kloosterman-Salih sums in analytic number theory. Okay, but I find it incredibly fascinating to compare objects in Euclidean setting and in the discrete setting. When you compare them, you'll learn a lot about both. Okay? And so in conclusion, if m doesn't equal to 0, the indicator of the Fourier transform of the sphere at non-zero frequencies is bounded by a constant, which is actually 2. 2 times n to the power of minus a half. Okay? Yes.
Patrick, those spheres, how do they look like? It is possible to visualize the sphere in Z and 2, for example, on the plane.
So I could, instead of giving you a fancy answer, let me just say no. So because it wraps around. So I like computers. So at least for circles, you can do a visualization, and it looks really pretty. It has patterns. How much intuition you get from that is debatable. It should say something.
Some regularity, probably not. It's not very difficult to draw.
So it's not difficult to draw, but it's a great question. It's a question that I've asked myself many times. So the key feature of the Euclidean circle, as far as problems of this type are concerned, is the curvature. You said the way the circle is different from, let's say, a boundary of a square is that the curvature is positive, just in the sense of calculus curvature, right? However, in the finite setting, curvature is not the right thing to think about. The right quantity in the finite setting is the additive properties. So here's the property that the discrete circle, if n is prime, and the Euclidean circle have in common. So the circle in Euclidean space has the following beautiful property. Suppose you take 4 points, x, y, x prime, and y prime on the circle. And suppose you consider the equation x plus y equals x prime plus y prime. Maybe this is a good time to draw a picture. It's not clear I can actually make this work, but because everything I touch that's electronic just doesn't work. But let's try it. So circle, right? And let's say that this is x and y. And let's say that this is x prime and y prime. Then if we add x and y, we get a point over here, right? This is x plus y. And if we add x prime plus y prime, then we get a point over here. Okay? So indeed, if x plus y equals x prime plus y prime, then either x equals x prime and y equals y prime, x equals y prime and y equals x prime, or x equals minus y and x prime equals minus y. Okay, so this is just high school geometry.
functional analysis. Yes.
Well, just elementary geometry. Yeah.
Convexity of unit ball.
Right. But here it's right. It's even more pinpointed than that, and the same property holds in ZN2. Okay, so it's somehow the additive properties of the circle that are the right, gives you the right analog of curvature in this setting. All right.
You vary the radius. Does it?
That's a good question. So,
or not?
So this is not a metric space, right? Yeah. So beautiful thing about a circle in ZN2 when n is prime is that all the circles of non-zero radius have the same number of points. And this is a great exercise. Well, so if you take any two circles of where the radius is a square in the field. So remember earlier we discussed why I didn't take a square root, right? So suppose you take two circles where the radius is a square. Then you can easily bijectively map one circle into another, and this tells you that they have the same number of points. If you take any two circles where the radius is not a square, and by radius I mean radius squared in normal parlance, right? Then once again, you can establish a bijective correspondence. What is a little bit trickier and requires a little bit of abstract algebra, so kind of baby Galois theory, is to show that you can map a circle of square radius to a circle of non-square radius and still get a bijection. And this is a great exercise. Even if you've never had abstract algebra before, who cares? Try it anyway. What is the worst thing that can happen to you? Okay? Yes?
Explain how did you get here?
Sure, no problem. This is great. So, here we simply, so take OS here for the moment, right? Then this sum will be 0 unless norm x equals 1, because we're summing over all the characters. Then we notice that it's enough to take s not equal to 0 if m is not 0. Because if s is 0, we're summing all the characters here. And we get 0. So we can take s not equal to 0. Now we complete the square, right? And so we take sxj minus xjm. We factor out s. And we get s times xj minus mj over 2s quantity squared minus mj squared over 4s squared. Okay?
So you mean to just multiply two characters? And, yeah.
Oh, yeah. Well, I mean, these are just exponentials, right? These are exponentials. So now you make a change of variables. You send xj to xj minus mj over 2s. And then you get the line on the bottom. Okay? So then we sum in x. If we sum in x, that's a product of Gauss sums. Okay? And each Gauss sum is going to give us square root of n times a unimodular function. Okay, functions of complex modulus 1. So we have n to the minus d over 2 in front. So after we've done this, d times, this is why we're left with n to the minus 1, because n to the d over 2 kills n to the minus d over 2, and then we end up with this sum. Does that make sense? Sure. Okay, and as I said, one has to use a very sophisticated result from analytic number theory. So the first few proofs used very sophisticated algebra, cohomology theory. Finally, an elementary argument was found by Stepanov about 20 years ago, but the word elementary here should be taken with a grain of salt. It's still 25 pages of hardcore calculations, and Stepanov, in the classical tradition of the Moscow school, did not include all the details. Okay. And the proof is correct. It's just used. All right. So then once again, the Fourier transform at the non-zero frequencies is bounded by 2 times n to the minus a half. Okay? So let me try to put this into perspective. So in both cases of the sphere and the paraboloid, okay, if m is not equal to 0, the Fourier transform is bounded by a constant times n to the minus d over 2. That comes for free because it's there in the definition of the Fourier transform, times the square root of the size of s. This is an example of the so-called square root law for exponential sum. Now, square root law is not a law because it doesn't always hold. Okay, but it's a principle that if you take a sum of sufficiently well oscillating terms, that they behave like independent random variables. Okay? And if they truly behave like independent random variables, you expect to get square root of the number of terms. The terms have modulus 1. So this is why you get the size of s to the power of a half. Now, this is certainly not always true, but it's an example of this phenomenon. And so there's an interesting question arises, and whether such an estimate can ever hold in a non-field setting. And for the next few minutes, I'm going to be a little bit sketchy, but I just want you to get a flavor for things that are going on. So if you've never dealt with characters in a non-commutative setting, don't worry. I just want you to get a flavor. Obviously, if anybody wants the details, I'm happy to discuss it later. Okay? So here is a theorem, and this is joint work with Brendan Murphy and Jonathan Pakianathan in 2014. So here you have a sequence of finite rings, not necessarily commutative, okay, such that the size of each ring is odd. We can handle the even case also, but for the sake of simplicity, I'm sticking to the odd case. And the size is going to infinity. So you have a sequence going to infinity. And now you take the Fourier transform with respect to characters on not necessarily commutative rings. If you know what that is, you know that they exist. Otherwise, please take my word for it.
That's why you have because it's not commutative.
Right. And suppose that the modulus is still bounded by some constant times the size of the multiplicative group of the ring to the power of 1/2. In other words, suppose that we have the same phenomenon with a uniform constant as we saw in for a paraboloid or for a sphere. Okay? Then our eyes are eventually finite fields. In other words, you can't get the square root law, at least for a hyperbola, and this argument extends to parabola, and it extends to a circle, etc., etc. So you cannot have square root cancellation in the presence of zero divisors. Okay, so you have. I also wanted you to see this because here, algebra, number theory, and analysis all meet. Okay? Yes. Please.
Eventually, in this case, means that from some index, you can only fuse.
That's right. That's right. Because the reason you have to phrase it this way is because of this constant. By increasing this constant or decreasing this constant, you can play around with the index, but that's purely artificial, right? Make sense? Okay. And and this is a result by a PhD student at CUNY, Nathaniel Kingsbury. He's a second-year PhD student. You should remember this name. This is a very, very bright guy. And so he proved the following result. Again, I stated in a slightly sketchy fashion, but I want you to get an idea. So f of x1 through xd minus 1 is a polynomial in z of x1 through xd minus 1. So then Vf of r is a solution set of xd equals f of x1 through xd minus 1 over a finite ring. So it's a surface over a finite ring, if you wish. And suppose that a sequence of finite rings has the property that the Fourier transform again satisfies the square root law cancellation. Then, once again, you eventually get fields except for a small number of exceptions. So there actually are some exceptions, which are certain matrix rings. Okay? But my point here is largely that square root law cancellation is either impossible or at least very rare in the non-commutative setting. Okay? And for this particular result, one cannot fake algebra. One actually has to use very heavy duty. Okay. So let's go back. And so remember, our goal ultimately is to talk about signal recovery. But one cannot do signal recovery with the Fourier transform in a meaningful way without having a good feel for the Fourier transform. Because Fourier transform is what we are transmitting after all. Okay? And all right, so suppose that you have a set S, and okay, one thing that I'm realizing here is that usually when I take the Fourier transform of an indicator function, I call it 1S hat. And here I use the notation that I used up until a year ago. Okay, anyway, so this is the Fourier transform of an indicator function. So this is the second typo. And this is after I've been through these slides, I don't know, maybe a dozen times. Okay, so suppose it's bounded by a constant that we call C Fourier, n to the minus d over 2, times the square root of the size of S. So in other words, we have the square root decay, but be careful, there's a constant C Fourier, right? So this constant may be large. So now is a very, very important notion. Suppose we want to compute the L4 norm to the power of 4. So the sum of the Fourier coefficients raised to the power of 4. Oh, also one thing I should ask, how much time do I have? Huh? No, seriously. 5:30, an hour? Is that what you envisioned, or?
1 hour, but up to 1 hour and a half, or
okay, let's do an hour and 15 minutes. Okay, maybe that's okay. So let's take the summation of the Fourier transform of S to the power of 4. Okay, and again, we take the four-fold sum and we write it out. So we get a summation of chi of, this should not be z, this should be m. Chi of m dot x plus y minus x prime minus y prime. And the sum in m is missing. Okay? Okay, the sum in m is missing. So there should be a sum in m in front, and this letter should be m. This was added last night. This is what happens. Okay, and so when you sum in m, you get 0 unless x plus y equals x prime plus y prime. Okay, so what we get is n to the minus d and the number of additive quadruplets. Okay, this is called the additive energy of a set. Additive energy of a set is the set of quadruplets, x, y, x prime, y prime, so that x plus y equals x prime plus y prime. Roughly speaking, it measures how much additive structure a set has. Yes?
E of x, y,
these are indicator. How did this happen? I'm sorry. I'm going to blame this on beer last night because this was added last night. This should be F. All right, we don't have to go into details. Okay. This is S. So this should be S of x, S of y, S of x prime, S of y prime. Sorry. And indicator function of S. And okay, so you see this, and then you get n to the minus d times the additive energy. So this time it's written correctly with S. So in other words, additive energy is equal to n to the d times the summation of the fourth powers of the Fourier transform. Okay? And by assumption, the right-hand side is bounded by n to the d, C Fourier squared. I know what happened. I copied it from the notes from more than a year ago when I was still using this notation. Okay, anyway, n to the minus d times the size of S times the size of the Fourier coefficient squared. Okay, because we simply took, you take the S hat of M to the fourth, and you take out two of the powers, because remember, we assumed that S hat of M is bounded by C Fourier n to the minus d times this S to the 1/2. Sure.
Number lambda of S.
Mhm.
Actually, it means the number of parallel vectors to S, right? So if you move this X prime to one side to the other, you get a represented vector.
So I know it sounds like I'm being difficult, but I really would caution you against Euclidean intuition.
Doesn't matter.
Yeah. No, oh, sure. Okay, that's fine. Yeah, it's simply the number of quadruplets where, but yes, you can think of it this way. Yeah. So it measures the additive structure. It measures how close your set is to a plane, in some sense. Okay? Or how far. And so we estimate the sum of the fourth powers of the Fourier coefficients by the second powers. And by Plancherel, this quantity equals C Fourier times the size of S squared. And we conclude that additive energy divided by the size of the set squared is bounded by the Fourier constant. So if the Fourier constant is like a number, like 5, that tells us that the additive energy is bounded by the size of the set squared. Now go back and take a look at the additive energy. So the size of the additive energy is always at least 3 times the size of S squared, because those conditions can always hold on the board, right? And the size of additive energy is at most the size of S cubed, because you can always fix 3 of these numbers and solve for the fourth, right? So what we are saying here is that if the Fourier constant is some fixed number, in other words, we have optimal Fourier decay up to a constant, then the additive energy is up to a constant as small as it can be. So you cannot have very much additive structure. Okay? Now, one cautionary note, and this is going to come up later, not having a lot of additive structure doesn't mean that there is no additive structure. So the picture you might want to have in mind is you're in Zn2, so in the plane, and you take a set of size n to the 3/2, which is extremely nice in terms of additive structure. So this equation is never satisfied except in trivial cases, and then you add a line. This will not affect the estimate by that much, but you still have a subset that has very bad energy properties. And this is important. Okay? All right.
Why it is called energy? What is energetic in this definition?
What is energetic in this definition? So it is quite often happens in mathematics, an incredible stretch. It's an energy because it's expressible in terms of the Fourier coefficients raised to the power of 4. If you take Fourier coefficients and raise to the power of 4 and replace it by an integral, then you have, let's say you take a Fourier transform of a measure, take a Fourier transform and raise it to the power of 4 and integrate. Now replace the power of 4 by the power of 2 and throw in, let's say, norm C to some negative power. Then you really get energy from geometric measure theory. Of course, then you might ask me, why do they co-at energy? And the reason they co-at energy is because in the case when the power when the power on the Fourier transform side is suitable, then when you go back to the space side, you get a double integral d mu x d mu y divided by norm x minus y, and this is Newtonian energy. So this is, it's like the word normal in mathematics, right? It's almost a swear word, right? It means whatever you want it to mean, right? But in this case, there is a connection to energy, which I just described, but it's pretty long-winded, right? Okay. All right. So now let's go back to signal recovery. Okay? And so the first thing that I would like to do, I think it sort of helps psychologically. Instead of diving into advanced methods, I want to convince you that signal recovery is possible. When I first heard about this problem, when somebody described it to me, I had trouble believing on the organic level that this can really be done. Because think about it, a Fourier transform is sent, some of it is missing. How could you possibly get it back? My guess. And so I was introduced to this by my co-author, Azita Maeli, and she asked me this because she wanted to see my reaction. And my reaction was, sure, you can approximate it. And the approximation depends on how many terms you're missing. That's a reasonable guess, but it's incorrect. You can actually recover it exactly. And the first thing I'm going to do is I'm going to give you an elementary setup where it will be very clear why this is possible. This is what I had to do to understand it. Okay? So you take an indicator function of a set E, okay? And suppose that the Fourier transform is transmitted and the frequencies in S are unobserved. Okay? All right. So one thing that I always do when I do mathematics is I always use the most elementary approach possible, right? I don't use advanced techniques that I know or anything like that. I never do that. I always try to do it at the level of 6th grade mathematics. And if that doesn't work, then I slowly go up. I'm really not joking. Okay, so the indicator function of E is n to the minus d over 2 times summation of chi of x dot m times the Fourier transform. And of course, you can, so the frequencies in S are missing. So what does that mean? That means you can write the inverse Fourier transform as a sum over frequencies that you have, so m not in S, plus the sum over the missing frequencies. Okay, now we mentioned before that common sense is your friend. The sum over the missing frequencies, they are missing, which means that there's nothing we can do there except estimate and hope for the best. So we'll take that second term, we'll estimate it, and what happens? So it's first plus second. And the second term, by the triangle inequality, we're not even using Planck-Charel. Triangle inequality. This is bounded by n to the minus d over 2 times the number of terms in the sum times n to the minus d over 2, which comes from the definition of the Fourier transform, times the size of E. Okay? So we twice use the fact that if you want to estimate a sum, it's bounded by the largest value times the number of terms, which I claim is all humans can do. Everything else just reduces to this. This is really true. Think about it. Okay? So you have n to the minus d times the size of E times the size of S. And suppose that this quantity is less than a half. Well, if it's less than a half, we go back to this first term, right? So this is the term over known frequencies. We take its modulus and we round it up to 1 or down to 0, right? Imagine you get 0.6, then you know it had to be 1 because the error is less than a half. Okay? So this tells you that it's possible. And then you might wonder, why not just use this method in all situations? Because we used in a strong way that we are dealing with an indicator function of a set. However, this may or may not come up in my lecture tomorrow. If it doesn't, it will come up in Kiev. It's that if you have a general function, you can quite often discretize it. And this has applications to time series analysis. Okay? You can often discretize it and use this trick again. Because as long as you know that the values of your functions are delta separated, you just need to estimate the second term, but not by a half, but instead you need to estimate it by by delta over 2. Yeah, delta over 2. I was about to say 1 over 2 delta. That's not correct. Okay. All right. So now you know that this works. And let me, yeah. Oh, this is great. We have time. Okay. And so this gives us exact recovery. Moreover, not only does it give us an exact recovery, it gives us a simple algorithm. This algorithm can be coded in approximately 10 minutes, and it runs very fast. Okay? No, seriously. Okay, true, but I use ChatGPT only after I've written my code, and then it speeds it up. But if you use ChatGPT to write your code, you will eventually run into such incredible problems. You don't even want to think about it. Okay, because you lose control of your own code. Yeah, you don't believe me, do you? Okay, you'll see. Okay, so the question now is, what happens if we consider general signals? Okay, and so here we are going to use a method that was for a long time attributed to Donahoe and Stark. So Donahoe and Stark, so this is a very instructive story. Donahoe and Stark in 1989 wrote a beautiful paper, not taking anything away from them, where they do many things, and among them, they introduced a method that I'm about to describe. However, so there's one peculiarity of the United States is that we really dislike learning foreign languages. And it turns out that in 1973, Matolcsi and Zux, so two Hungarian mathematicians, in the French language, published an exact same proof of this that was somehow flew under the radar. It's actually quite amazing because both are very strong mathematicians. And they didn't, even in 1989, when Donahoe-Stark paper came out, they really didn't say anything. They just didn't care. And I found out about this 6 weeks ago. No, well, maybe in July when I was in Cambridge. And anyhow, so here we're going to use the classical uncertainty principle. So what does it say? And I'm going to prove it, that the support of the signal times the support of the Fourier transform of the signal is bounded from below by n to the d. The proof is simple and generic. It works in any locally compact abelian group. Did you have a question?
So there is a continuous version of uncertainty principle which compares the norms, not the size of supports, but the norms. There must be analog of this in discrete setting, comparing the norms.
Absolutely. And in fact,
different type of uncertainty principle, or it's the same, just it should look.
Yeah, so in fact, the proof of the classical uncertainty principle contains at least a simple version of the norm principle, and we're going to see this in a moment. But yeah, you're absolutely right. Yeah. Okay. So suppose that the signal is supported in a set E with frequencies in S unobserved, right? So this is the initial setup. Okay. And so what does it mean? So this is actually the hardest part, is to conceptualize what it means that we cannot recover the signal. Okay? What it means is there's another signal in our class. What is our class of signals? It's the class of signals with a given support, given size of the support. Okay? That's a weaker condition. We could assume that they have the same support, but then we would need to know what that support is. So it's better, it's more general to assume that they simply have the same support. And the Fourier transforms agree when M is not in the set of missing frequencies, because we have no idea what's going on there. Okay? And F is not identically equal to G. If such a G exists, then indeed we cannot recover the signal uniquely. Okay? And so, as we were discussing with Rostislav earlier, you solve this problem the way you solve half of the problems in first-year graduate analysis. You take H equals F minus G. And so then it's clear that the Fourier transform, well, the support of the Fourier transform is in S, because F hat and G hat agree away from S. Okay? And the support of H is at most twice the support of F, because H is F minus G. So if F is 0 and G is 0, then evidently H is 0, right? So we applied the uncertainty principle, and it tells us that the size of the support of F times the size of the missing frequencies is bigger than or equal to n to the d over 2. Therefore, if we assume the opposite, we win. So if we assume that the size of the support of F times the size of the missing frequencies is less than n to the d over 2, we must have H equals 0, and hence the recovery is unique. Here's what I'm not describing, because I decided not to focus on this in these lectures, is the actual recovery mechanism. There are many, and none of them are particularly good, or not as good as one might want. Anyway, that's a separate discussion. Okay, but for example, since everything is finite, if you really wanted to convince yourself that a recovery mechanism exists, it is not hard, but this can hardly be called an algorithm. You'll see why. You simply consider all possible functions supported in a set of this size. You understand that once this sentence is uttered, all pretenses to practicality are gone, right? Because this is an exponential time algorithm. And then you solve the problem by the least squares method. There are better methods, but the point is that algorithms exist, and we've just proven uniqueness. Okay. Does this make sense? Okay, this is a really simple and beautiful idea. Okay? And so let's see, in the time, I think I just have enough time to discuss a few things about the classical uncertainty principle. So the classical uncertainty principle is, in general, sharp. And there are many ways to see this. And it's even sharp when n is prime, at least in higher dimensions. Okay? So take n to be an odd prime, and S is a k-dimensional subspace of Z and D. Okay? Here, the Euclidean visualization works. Okay? Because the Fourier transform up to a factor, n to the minus d over 2 plus k, is an indicator function of the orthogonal subspace. This is why I took n to be prime. If n is not prime, one can still make sense of this, but one gets a small headache. Let's not do that. Okay? And so since the size of S times the size of S perp is n to the d, it's an orthogonal subspace. The classical uncertainty principle is sharp. Okay? And so what we are going to see is that even though there are examples where the classical uncertainty principle is sharp, this is almost never happens. For a typical set, one can prove a much stronger version of the uncertainty principle. Okay? And this will be the subject matter of tomorrow's lecture. But let me go ahead, let's see. Let's just go ahead and finish off the lecture by proving the uncertainty principle, because it uses exactly the techniques that we've developed in this lecture. So this should read pretty easily, okay? All right, so we write h of x as an inverse Fourier transform of its Fourier transform, except that we can sum over S, because by assumption, the Fourier transform is an S, okay? So by the triangle inequality, here I could have used Cauchy-Schwarz, but I decided to use the triangle inequality because I want to put an accent on elementary methods. By the triangle inequality, the modulus of h of x is less than or equal to n to the minus d over 2 times the size of S times n to the minus d over 2 times the summation of the moduli of h of x. Okay? Okay, so I'm committing a pedagogical faux pas here because I'm using x as an active variable on the left-hand side and x as a dummy variable on the right-hand side. But, you know, I think everybody in the room probably programs computers, so this is a local variable, right? We're okay. All right, now we sum both sides over x and e. Oh, sorry, there's a question from the back. Yes. Couple of slides back. Okay. Oh, because it's an orthogonal subspace. It's just linear algebra. If you have a, for example, let's say you're in 2 dimensions and you have a line, and you look at the orthogonal line, then the dimensions add up to 2. Or if you're in 3 dimensions and you have a 2-dimensional plane, then the orthogonal space is a line, and once again they add up to 3.
The area of Lenin.
Let's find area of who?
Lenin.
Oh my God, did we have to bring him up? Okay, but go ahead.
Exactly this. You should multiply length of Lenin by width of Lenin, right? Until obtain area of Lenin.
Beautiful.
Площадь Ленина, как найти?
Площадь Ленина. Wow, this is not going to spoil this thing for me, but it's coming close. Okay, sorry. There's another question from the back. Is everything okay? Are things good? Oh, no, but the line, the orthogonal space to a line is not a line, it's a plane. You then day it up, yeah. Yeah, you look at all the vectors. So for example, in R3, so take the z-axis, and then you look at all the vectors in 3 dimensions, such that the dot product with 0, 0, t is equal to 0. And this is, of course, any vector where the last coordinate is 0 and the first 2 coordinates are non-zero. So it's going to be a comma b comma 0, and that's just the plane, the xy axis. Make sense?
So just any vector in N and D can be written as a sum of the components, and we just count the cardinality of subspace and orthogonal complement, because each pair from there corresponds uniquely to the element of ND.
Right. You see, unique decomposition into orthogonal subspaces. Okay. All right. So, okay, so let's go ahead and prove. So we took H, wrote it in terms of its Fourier transform, restricted the sum to S because the Fourier transform is supported in S. By the triangle inequality, the size of H of X is bounded by n to the minus d over 2 times the size of S. Again, we are dominating the sum by the largest term, times n to the minus d over 2 times the sum of moduli of H of X. And now we sum both sides over X and E. Okay, if you sum the left-hand side over X and E, you get the size of E on the right-hand side, and then you cancel the summation of moduli of H of X. Of course, you should complain. What if I'm dividing by 0? Well, if I'm dividing by 0, then H is identically 0, and we can go home. Right? All right. And so then you simply cancel the L1 norms, and you get the size of E times the size of S is bigger than or equal to n to the d. So I hope that the uncertainty principle has been demystified for you for life. There's nothing complicated going on. Okay? So math is usually less complicated than we think. It's we that make it complicated, right? Okay. All right. And this, I think, is a good stopping point. So tomorrow we are going to see why this theory that we've seen so far, that was developed by Matolsky and Jukes and Donahoe and Stark, while it's beautiful theory, in most cases one can do much, much better. And I'm going to stop here. Okay.
Thank you very much. So are there any questions from the room?
As I understand, the possibility of such recovering lies in the fact that you have restrictions on the values, that just 0, 1,
yeah.
And from the point of information theory, so somehow the information is transmitted in this form that you can recover. Okay?
Yes.
So from information point of view of information theory, could you evaluate the amount of information in the fact that values are 0, 1, and amount of information that some frequencies are missing? So what is
so okay, okay, this is a long story, but this is a fantastic question. So in the end, all of these questions ultimately tie into the CKS complexity, so the heightened Kolmogorov-Solomonov complexity. And but how exactly to do this is not clear. This is a difficult problem, but it must be, because I don't want to sound banal, but almost every question in mathematics is tied into CKS complexity. And I've been trying, coincidentally, over the last 6 months, pretty hard to express everything that we've discussed in that language. And this is still a work in progress. But I think it's a great question.
how much information is lost in this way? I mean, that question.
Sure, I can write it in terms of complexity, but I want to be able to do more than write it, right? I want to actually be able to use techniques of complexity theory and bring them to bear in this problem. And this I have not succeeded in doing yet.
Could you please, in few words, maybe explain why do we actually consider these types of functions as signals? Like, what's the connection to regular signals?
Sure, no, it's it really so for example, if the dimension is 1, then if the dimension is 1, then this is just a classical signal, right? If the dimension is 2, then you can think of these as images. If the dimension is 3, then these are also images, but there are also different applications which I may or may not get to tomorrow, probably not. But it's in terms of time series analysis, higher dimensions make sense because you can think of it as time series with regressors. And this theory, believe it or not, actually has real life applications to data science.
Thank you.
I have a question.
Thank you. So you wrote us theoretical formulas, but I have more practical question. For instance, what is the order of number D, for instance? Or for instance, let's assume that you transmitted a signal and you, for instance, lost 10% of the signal. So how should you how big should be number D in order to successfully recover the signal? Are there some formulas that connect these numbers? Or
excellent question. I understand your question, and the reason I'm smiling is because I don't want to oversell this. These are mostly theoretical results. I've mentioned a few applications to time series, and those are very concrete and particular, right? But in terms of the signal and signal recovery that you've seen so far, from the practical standpoint, this is not how it works. So every time, so I've been working on this for about a year with Azita Mayeli, and every time we came up with a new result, I would mention it to my oldest son, and within an hour, he would exhibit examples, computer code and examples that show that in real life, you get much better recovery conditions if you're willing to sacrifice certainty by a tiny bit. In other words, all of these results are based on the assumption that you want to be 100% certain that you are recovering the whole signal. If you're willing to be 99% certain, you can do much, much better. So in other words, I don't want to oversell practicality of this. There are some aspects of this that really are practical. For example, we have a result on recovering missing values of time series based on this type of analysis, and that really does work. And it compares favorably to at least to the sort of free packages you can lift off the internet. But in general, this is not how you want to recover signals. And people who do this for a living, I'm certain that they don't do it this way.
Any further?
Yes.
So again, about terminology. Uncertainty principle, so there should be some intuition behind this terminology, of course. And is there any relation to physical uncertainty of Heisenberg, for example?
Oh, there is. Yeah. There is, but this is not. There is, but this is a long story. I can review it. It would take me half an hour to review, and I'd be happy. I can do it tomorrow, for example. But yes. Yeah, I would need to review. I haven't thought about it in a while.
Geometrical, or not geometrical, any intuition in this uncertainty principle. So what is this? Okay, so the way I think about the uncertainty principle, so here it's revealed that I'm actually by training a harmonic analyst. So in Euclidean space, imagine that you want to compute the Fourier transform of an indicator function of a rectangle that is A by B, let's say in R2, okay?
in practice, you never want to do that. So instead, you take a smooth cutoff function that is supported, that is 1 on this rectangle and 0 under a slightly. So then you compute the Fourier transform, and what do you get? You get roughly, first let me say what it is roughly, and then let me tell you what it is exactly. Roughly, you get the area, which is A times B, and then you roughly get an indicator function of the dual rectangle, which has sides 1 over A and 1 over B. Dual rectangle is a rectangle which is pointing in the orthogonal direction, and it has sides. It has sides that are reciprocals of those. No, but there's no lattice here. This is just R2. It's just R2. And this is a completely direct calculation. Then you see that the area of the dual rectangle times the area of the original rectangle is 1. Now, what happens in reality is that if your function is compactly supported, then the Fourier transform cannot be compactly supported because complex analysis has not been canceled, right? However, the Fourier transform is concentrated in that dual rectangle. So this is the physical intuition. To me, so there was this dark past when I studied physics. It's a skeleton in my closet. Anyway, but even then I found this argument more compelling from a physical point of view than the original Heisenberg uncertainty.
I have another question.
Yeah.
So assume the original signal has some smoothness, which means that, say, you have a smooth function not on ZD, but on, I mean, Zn, but on 0n times.
I see. So you want to
power d, yes.
Uh-huh.
You have just trace, just evaluate the values of the discretize the function. So initial function is smooth. Yes. So there is some smoothness behind this discrete signal in this sense.
Understood.
Yeah. And assume you have some noise. So now, or even without noise,
got it.
Does these help you, or does this information can it be used to improve the bounds, the constants you have here?
Okay. Well, this is exactly what, properly interpreted, this is exactly what tomorrow's lecture is about. However, the right scale turns out not to be smoothness. And from a common sense point of view, it makes sense, right? Because in any sort of a practical situation, it's difficult to tell if your function is smooth or not. It's the LP scale that plays the role, much like it does in your result and the distribution of zeros, right? So what we're going to see tomorrow is that the LP scale can be used to improve these results, provided that the set S has the right structure.
Okay, so personally, me.
So many questions.
No, it's great.
So you presented here just discrete finite theory, and of course one can ask about limit cases, right? So when you take n to limits, you obtain something interesting in the duality square z. Or interesting implication in limit case of all of this.
So there are two. So there are two parts to my answer. So first of all, the reason n is finite here is because in real life signals really are finite. However, in the continuous case, this does have manifestations. They're reasonably complicated, and I actually removed those slides. But I'll be happy to discuss this. Yeah, in the continuous setting. In a continuous setting, for example, you can ask the following question. Suppose you have an indicator function of a set, and suppose that the Fourier transform is known except, let's say, a delta neighborhood of the sphere. So a simple situation like this. Then the question is, can you recover your original set, up to sets of, up to almost everywhere? Can you recover your set? And it turns out that the answer is yes, provided that the measure of the set, let's say it's a compact bounded set, if the measure of the set is bounded by 1 over delta. So if you're missing delta neighbor of the sphere, which has volume delta, then you're okay if the volume of your set is less than or equal to 1 over delta. And in the case of a sphere, you can improve 1 over delta to 1 over delta to the p, where p is almost 2. It's 2d over d plus 1. And this goes to the, not to over-dramatize this, to the heart of modern harmonic analysis, the so-called restriction conjecture. So if one generalizes this problem to Euclidean space, one very quickly runs into some very, very deep problems in modern analysis.
It's just duality between real line and real line. There is also duality between z and circle, or z to power d, and on this level, what's correct?
I see. On the level of taking limits, things work out, because then you essentially get, so what is the limiting theory of this? It is essentially Fourier series on the torus. And then you can work out examples and everything connects. Everything connects. It's not, again, it's not clear what practical impact that has, because signals should be finite, but theoretically they connect and you get the results that you would expect.